This is Sean from the MLabs Purus team, and in this video I'm going to go over our research that we've conducted to show for the Catalyst system that we have reached our milestone goals for Milestone 1. So just as some general background information, our project, Purus, is an attempt to create a UPLC backend for the PureScript compiler. And what that means is that you'll be able to write PureScript, and we'll utilize a bunch of existing machinery from the compiler to compile that PureScript down to eventually untyped Plutus core, which is the language that executes in the script interpreters on the Cardano blockchain. So we identified kind of 6 broad research areas that we needed to come up with answers to before we could proceed to actual development of our compiler backend. And so I'm just going to go through those in turn. This is kind of irreducibly going to be a bit technical, and that I generally assume that the person watching this has some general familiarity with Plutus development on Cardano, simply because we don't have enough time to kind of go from scratch here. I mean, this is the kind of thing you could take like multiple college classes on and, you know, work as a developer and still not really understand everything. So I apologize for that, but hopefully this will be clear enough to show that we have been making progress towards our goals. So the first problem that we needed to do some research on is the approach to data encoding. Right, and as it says here, data encoding refers to the way in which data types from PureScript, algebraic data types, are compiled down to UPLC code, right? And one of the biggest problems that we have to figure out is how to handle row-type polymorphism. So PureScript, unlike Haskell and unlike most other programming languages, uses a system of records where the records are backed by row types or rows of types. And these are kind of some examples of polymorphic row types. And a polymorphic row type is a, in the context of what we're concerned about here, it usually manifests as you have a function over a record with some known fields, and you don't care what the rest of the fields are. So the polymorphism consists in the fact that there's a type variable here that represents the rest of the row, right? And I guess I don't need to go over all of this. We considered 2 broad solutions. So in general, aside from records and the row types that constitute their type system, everything else is pretty straightforward because ultimately there are known techniques for encoding kind of less exotic sorts of types, so those aren't really a problem, so we're not going to discuss them here. And we considered 2 basic approaches to deal with row type polymorphism, and the first one was to desugar record accessing, record updates, right? Because that's what we really care about. Here, using a type class. And the type class would look something like this. And this is, Haskell has an internal type class in the GHC compiler, the hasfield type class. And the Haskell implementation of row types in the data.row library from the row types package uses a similar sort of constraint. Yeah, so basically what we would do is we'd replace every occurrence of something like this, where we have an open row, or actually this is a better example. where we have an open row with some type class that says that the function is constrained to work on records, or I guess objects if you're looking at PureScript from a JavaScript point of view, which have a known field with a known value type. Okay? So, and this is if we had a type class like this, right, where the class is parameterized by the name, the label of the field, the type of the value at that field, and the row type that contains that. We could create, we could desugar those open rows into a type class constraint. Right, and this, I won't go too much into detail here because ultimately we didn't choose this approach, and also because it's somewhat complicated to explain if you aren't familiar with the Haskell analogs, right? So yeah, this is one thing we considered, and we came to realize that it would work, but the problem is that the this is a kind signature right here for the type class, right? And we don't have symbols, I believe, or row types in either type Plutus core or PIR, the Plutus intermediate representation, right? So that's the real problem with this approach, is that we can't actually represent the arguments of the type class, and so while it would be possible, it would require some kind of ad hoc machinery, which doesn't seem very fruitful. And so the second solution, well, let me explain something up here first while I talk about the second solution, right? So this type foo row, right, is parameterized by this type variable a, which represents some unknown row of types. And when we use this type synonym, we expect to get, we don't care usually what the a represents, but we want to be sure that we're working with a row that has a label b with a value of type c, right? And so one nice thing about the fact that we're compiling Plutus scripts here is that by the time we do our final compilation pass, due to the nature of the type signatures involved in a Plutus script, even if there aren't explicit types, it kind of has to work on specific types in order to function as a Plutus script. And one of the nice features about compiling a Plutus script, which is either a validator or a minting policy, is that there are no type variables. So we know the types of everything, right? And this is important because in order to like do the final compilation where we're accessing a field from a record, right? Like retrieving the value at the field, or we're updating a record or something like that, we need to know kind of where the label of the field that we are updating is in a sorted list of all the labels. So we need to know its position in the record, right? And we can't do that unless we have all of the type information. But because minting policies and validators, minting policies and validators don't have any open type variables, we're guaranteed to always know the type of every record that we're working with. And so consequently, the solution that we opted for is to defer compilation, which means that we're going to wait to transform our syntax tree, the PureScript syntax tree from the PureScript compiler, into a UPLC type Plutus core, Plutus intermediate representation syntax tree until we are at a point where we know that there won't be any type variables, and then we don't have to worry about representing row types at all in the compiler output, because once we've reached the point where there are no type variables, we'll always know all of the fields that are in every record that we care about, right? Yeah. So again, solution 2 does force us into a particular design for the modules in the linker. Namely, we have to output modules that are modules in the pure script abstract syntax tree representation. But that's not such a big deal, and so our plan is to defer compilation here, right? The second milestone thing that we had to research was integration with lambda buffers, which we have somewhere. Yes. And yeah, we're going to add lambda buffer support and integrate with it. Lambda buffers is a schema language that has existing support for PureScript, and it should be fairly simple to integrate with lambda buffers, which should make it easier to share types between a Purus project and a project that doesn't use Purus, right? So not too much to say there. Type classes are the third, it'd be nice if this had an index, third problem that we said that we would research. And there's kind of only one obvious way to do this, right? So we have a type class, and type class constraints over functions. You can also have them over data types in Haskell, but I don't think we're going to have those here. And so this is an example of a type class constraint. And when you're writing code, you don't pass this as an argument. Everything to the right of this arrow is part of the actual signature for the function itself. But as we note here, you can kind of view the type class constraint as a sort of argument that is waiting to be applied. So pure here is a method of the applicative type class, and as you see here, if we need an applicative instance which will contain the pure method and the other methods of the applicative type class, we can rewrite this as this one argument function. It's an argument from A to MA, where M is a type constructor that's an instance of the applicative class. We can rewrite this to a function that, instead of having an implicit type class argument, takes an explicit type class dictionary argument, which contains all of the methods. Right, and this is just an example of that. Again, this is kind of the only sane way to do this, so not too much worth talking about here. Okay, so the next thing we had to figure out was the linker. And here we're using linker kind of generally to refer to kind of the final stage of compilation, I guess, since there's a little bit more here than just the linker. It's like the design surrounding the linker. But anyway, so the PureScript compiler, the way it works now, compiles code on a per module basis. And so it compiles, if you give it like 5 modules as input, it'll give you 5 modules as output. Maybe more than that if you have FFI, foreign function interface modules. I'm not sure off the top of my head. And it would be quite difficult to change this. We'd have to substantially rewrite large portions of the PureScript compiler, and so we're not going to do that. So the rough plan that we have is that we're going to do a 2-stage compilation process. And in the first stage, we're going to output an intermediate representation on a per module basis. And that'll be the existing PureScript internal abstract syntax tree, or a modified version of it that carries type information, because we need type information, right? So first we'll parse the concrete syntax tree, which is the first internal representation in the PureScript compiler, and then transform it into the abstract syntax tree. Again, this is just what the PureScript compiler already does. Then we will modify the PureScript compiler to output a typed version of its internal abstract syntax tree. And we need that because our current plan is to go to UPLC via PIR, Plutus Intermediate Representation. And we need type information, some of which we might not be able to reconstruct from the PIR after translating it. So we need the type information to do the translation, because PIR, like type Plutus core and unlike untyped Plutus core, is typed. Then we'll serialize these typed CoreFN modules and write those, right? So at the level where we're outputting a library and not an executable, we're not actually generating any Plutus core yet. We only generate Plutus core when we're ready to compile the script, the minting policy, or the validator. And then, so after we have the code generator for those typed CoreFN modules, we'll implement a second pass compiler executable, which will parse a main file, right? And this is going to be the script. So the main will either be a validator or a minting policy, or, I mean, maybe we'll make it so the name doesn't have to be main. We can name it validator or minting policy or whatever. That's not too important. So we parse the typed CoreFN, and then we resolve imports, and then we perform inlining. And so what that all means is that we take a bunch of modules that have been generated, and each of those modules will contain PureScript CoreFN code, and then we assemble them together into one kind of self-subsisting module with a main function where all of the type variables have been instantiated and we know all the types. And we inline, and then in the course of inlining, as we're applying arguments or whatever, we'll deduce the correct types for things like polymorphic rows, polymorphic records, which won't be polymorphic anymore because they'll be instantiated. And that's here we apply all of the type arguments and instantiate all of the type variables. Then we eliminate the object update and accessor expressions, perform any optimizations, which I'll talk about more in a second, convert to PIR, and then compiles down from PIR to UPLC. And we will likely not write a compiler to compile from PIR to UPLC because IOG has already written one that performs some optimizations, I believe, and is likely to perform more optimizations in the future. So this will hopefully give us another layer of optimizations after the ones in step 7. And then we serialize the Plutus script, probably in one of those like envelope formats for serialized on-chain data. And then somebody can, you know, do whatever they want to do with it that they normally do with the Plutus script. You know, you can, yeah. Okay. So that's the linker. So the fifth thing that we were going to look into was possible optimizations. And generally, our plan is to take everything that we can from PureScript Backend Optimizer, which is a tool that consumes the CoreFN. This is the untyped CoreFN, so it's not exactly what we are working with, but it's pretty close. And you can easily turn what we have into that, and shouldn't be too hard to go the other way, given where we're starting. Right, so what we think we can easily steal is a pattern matching optimization. So that's one thing. And I don't think it's worth going into too much detail about that. And additionally, we would like to try to implement stream fusion as an optimization. Yeah, that's something we need to research a little bit more, but Vladimir, one of our team members, has a implementation of stream fusion optimizations in PureScript already. So we think that we'll be able to adapt this, even though we can't borrow the existing PureScript backend optimizers stuff because it works on the JavaScript level. Yeah, and I don't think we wrote this, but we'll also need to perform probably a more sophisticated version of CSE, common sub-expression elimination, than PureScript currently does. Yeah, so those are the optimizations that we found, but again, we are more concerned about getting something that's kind of reliable than we are about doing all of the optimizations possible, at least in this grant. Should we come back to Catalyst in the future, one of the things that we are likely to do so for is the ability or the funds to produce more optimizations. And finally, software environment. So we're only going to support Linux. We say Ubuntu, and that's probably officially true, but we will likely support, informally at least, all major Linux distributions. All of our developers are primarily or exclusively use Linux as their system. I myself don't have access to a Windows PC at all. So yeah, we are going to not target Windows at the very least for right now. I mean, again, this is something that we may come back with a future request for funding for. And yeah, the real reason is just given the people that we have available and the fact that none of them have easy access to a Windows system, it just wouldn't be worth the extra effort. Yeah. Okay, so hopefully this suffices to show that we've been making substantial progress towards our milestones. If you would like to read the report yourself, you can find it in our repository under reports in the main branch, and I've been looking at M1 report. So yeah, bye-bye. I realized I forgot to mention something. So I talked about the data encoding for row types, but I didn't just talk about data encoding in general. So in general, we considered 3 different approaches for encoding data here being like things that are PureScript algebraic data types in a way that's representable on chain. And we considered 3 different options. The first is Scott encoding, and it's used in Plutarch, which is an embedded domain-specific language for writing Plutascripts. I believe it's also used in like the Plutus machinery that compiles Haskell down to Plutus core, right? And very briefly, it's very fast, and it allows us to store functions in data structures, which is important. I'll explain why in a second. And it's reliable, but ultimately we're not going to go with this for a few different reasons. It's not standardized, so it's very hard to tell from looking at a Scott encoding. Like if you just look at this, it's very hard to tell that it's supposed to correspond to just from the maybe type that this is a Scott encoded variant of. It's not intuitive. Again, it's very hard to read and look at and see what it's supposed to be representing. It might be slower than the SOP representation, though it's difficult to tell without better benchmarks than we have or have the capacity to produce. Yeah, it's difficult to lift expressions. I'm just going to skip these last 2. So the second encoding that we considered is the sum of products representation. And this is kind of new, and again, this is already way longer than it should be, so I'm just going to say that this is very close to a somewhat well-known way of doing generic programming in Haskell, especially with the generics SOP library, which many Haskell, I mean, we're all familiar with it, but I'm not sure how popular it is outside of MLabs. I think it's widely used, right? And ultimately, we're going to go with this. And the reason why we're going with the sum of products representation is both that it's possibly faster than the Scott encoding, maybe by a little bit at least, and it's much easier to read, and it enables us to store functions in data structures, which is a central concern for us, given that PureScript natively allows you to store functions in data structures. And yeah, we are not sure how we would prevent that, even if we wanted to do it, or what ramifications it would have for the language that we're making. So it just seems far smarter to store functions in data structures if we can, and we can. And based on conversations with IOG, we also believe that the SOP representation is likely to receive future optimizations, more likely than any of the other approaches here. Yeah, the only con is that it's not a native format, and that means that we have to convert into it. And this is also true of Scott encoding, which is to say that when we get the the datum or the redeemer or what have you from the chain, when it's running a validator script or minting policy, it's given to us in the Plutus data encoding we have to convert. And we should note that for very small scripts, the overhead of having to convert may make Purus less efficient and perhaps a worse choice than something else that operates on data encodings directly, like Icon. But for more complex scripts, we believe that the benefits outweigh the drawbacks of having to convert. The final option that we considered is the Plutus data encoding, and this is what Icon uses. The main reason that we're not using it is you can't store functions in data, which, again, PureScript is a functional programming language that intrinsically allows you to store functions in data. Also, the performance is quite bad, which, again, might not matter for very, very small, simple scripts, but for larger, more complex scripts, it definitely does matter. Okay.